Okay, then alpha systematics. One feature of alpha decay is that alpha emitters with large disintegration energies had short half-lives and conversely. അപ്പോൾ large disintegration energy ഉണ്ടെങ്കിൽ that had short half-life for that particle. For example, 232 thorium 1.4 into 10 power 10 years and half-life. Disintegration energy 4.08 MeV. And thorium 2118 218 thorium half-life 1 into 10 power minus 7 second ആണ്. Disintegration energy ഇവിടെ നോക്ക് ഇവിടെ 9.85 MeV. അപ്പോൾ large disintegration energy ഉണ്ടെങ്കിൽ then the particle is short-lived. A factor of 2 in energy means a factor of 10 power 24 in half-life. The theoretical explanation of this Geiger-Nutter rule in 1928 was one of the first terms of quantum mechanics. Geiger-Nutter rule എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ roughly speaking, it states that short-lived isotopes emit more energetic alpha particles than long-lived ones. അപ്പോൾ ഒന്നുകൂടി നോക്കാം. Geiger-Nutter rule എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ it states that short-lived isotopes emit more energetic alpha particles than long-lived ones. It is interesting that 235U, even Z odd n, is one of these extra long life types. If its half-life were 1000 times shorter, this important nucleus would not occur in nature, and we probably would not have nuclear reactor today. Okay. Looking for the moment only at the data for a greater than 212, we see that adding neutrons to a nucleus reduces the disintegration energy. എന്തുകൊണ്ടായിരിക്കും? Because alpha particle is a Coulomb. It is because of the Coulomb repulsion, which because of the Geiger-Nutter rule increases the half-life. The nucleus becomes more stable. A striking discontinuity near A equal to 212 occurs when N equal to 126 and is another example of nuclear shell structure. This also gives the basics of nuclear shell structure. We can compare the systematic dependence of Q on A with the prediction of the semi-empirical mass formula. We know that Q equal to binding energy of 4He plus binding energy of Z minus 2 A minus 4 minus B of Za, binding energy of Z, which is approximated to 28.3 minus 4 AB. This is the semi-empirical mass formula, plus 8 by 3s A power minus 1 by 3 plus 4AC Z A power minus 1 by 3 into 1 minus Z by 3A minus 4A symmetry into 1 minus 2Z by A square plus 3AP into A power minus 7 by 4. For 226 thorium, this formula gives Q equal to 6.275 MeV, not too far from the measured value of 6.45 MeV. 232 thorium equation, this equation gives Q equal to 5.71 MeV compared with Q equal to 4.08 MeV, while for 220 thorium the formula gives Q equal to 7.77 MeV compared with Q equal to 8.95 MeV. It is important that the formula gives us rough agreement with the decay Q value and that it correctly gives Q greater than 0 for heavy nuclei. The, it also correctly predicts the decrease of Q with increasing A for a sequence of isotopes such as those of thorium. Although it gives too small a change of Q with A, the formula is delta Q equal to minus 0.17 MeV per unit change in A. While for thorium, the observed average change is delta Q equal to minus 0.40 MeV per unit change in A. നമുക്ക് തിയറി ഓഫ് എമിഷൻ നോക്കാം, അത് അടുത്ത ക്ലാസ് നോക്കാം.